All right, welcome to our first study group of phase 3. Very excited. We're like officially more than halfway through the material of the course, which is insane. I feel like we just started. So phase 3 is the machine learning phase. And it is structured slightly differently from our last two phases. So I wanted to explain that, as well as expectations of how in depth you need to really know this stuff. So the first couple of topics in phase 3 are math topics. So linear algebra and calculus. They both play into gradient descent. Both are like the bases of how machine learning works. I would say out of these two topics, what I hope that you'll be able to explain is roughly how gradient descent works. Gradient descent works differently for every single model. I think some of you who did like some of the prep work did it in context of a linear regression, and I will be explaining it in that context as well. But for every one of the models that we're going to be talking about, they do gradient descent differently with different like cost functions, if that makes sense. So I think the most important thing to get out of here is just roughly how gradient descent is working. So that's what the next two topics focus on. Topic 24 is kind of like a random one a little bit. It is an extension of linear regression. So if you actually look into these are both Ridge and Lasso are two different models that are very similar to linear regression. It just helps account for overfitting, which is something that we didn't really talk about last phase. We talked about we talked about, all right, we'll see when something is overfitting, but not so much of like what are some real methods to account for overfitting. And Ridge and Lasso are two regressions that do a good job at accounting for that. So 24 takes us back to linear regression, but 25 all the way through 32, pretty much each topic is a different model. And that may seem kind of intense because every day is a new model, but my expectation of you guys is, so they are all implemented almost the same way. So they all have the very, very similar syntax. They're almost all in scikit-learn's library. Same syntax as we did with scikit-learn linear regression. You just like instantiate your model, do your model.fit, and you can do your model.predict in the exact same way. So technically, you don't have to understand how these models work to use them. Pros and cons. Pros is you can implement them without actually like figuring out the math behind all of them, which at this point is okay. One thing I will say is hopefully at the end of this phase, you will pick a couple that you really, that I guess you prefer, and then really hone in on those and then study those. Usually what I say is for our end of phase project, you will end up choosing one of these models to be your final model. So in contrast to what we were doing with the last project where you're doing like, linear regression over and over again, you're going to be doing just different models. And so similar how we were choosing our final linear regression model, you're going to be choosing a final model for classification. And that's what this project is. And then I would say just learn that model and maybe one more just to prepare yourself for interviews. And as we're going through it, I will kind of talk about each model, when they're used, when are they more or less likely used. So maybe you can use that to decide as well. One more thing to talk about, the project for this topic. Oh, and I guess before I get into that, topic 21, which is technically at the start of the phase, I put at the end, just because it's object-oriented programming. Those of you who have worked with object-oriented programming languages like, I think, Java, this will be familiar to you, but this is kind of like a completely separate topic that I'm thinking of, I think will make more sense at the very, very end. So that's why that is there. So the project for this phase is going to be individual. So that's something to remember, individual projects this time around. We're super lucky that our Christmas break falls right after the project is due. So similar to what we did for this past project, you're also going to have 2 weeks to do this project. Up to you whether you want to take it. You don't really need to take all 2 weeks, but you can. You do have the option this time as well. Let's see. So they are individual. And something that's pretty cool about this one is you actually get to choose between a few data sets. So we actually won't have the same project 23 times. So I think here there are 4 provided data sets that you can choose from. But once we get into, you know, the actual classification topics, I'll get more into it, but you can actually look for your own data set. So if none of these data sets appeal to you, this is the phase where you can start exploring what you're really interested in. Like if you know that you want to go into something like healthcare, you can go out and find a more healthcare related data set, and that will just be better for when you're interviewing in that industry. So it's something to think about. I will reemphasize this when we get there. But yeah, that's kind of an overview of the phase. Any questions about that? Awesome. Well, let's get started with linear algebra. Again, before we get started, any questions linear algebra related, if anyone has gone through the material yet?
Ish, I have a question.
Yeah.
For every topic for every data science topic, for example, machine learning, artificial intelligence, image processing, we can use all of these models, or each one refers to any specific topic?
Oh, that's a great question. So all of these models that we're going to talk about, logistic regression, k-nearest neighbors, pretty much all of these up until like support vector machines, these are all classification problems, a classification model slash algorithm. So if you just have a classification problem, you can actually use these models. Technically, image processing, you can use models like this. You can also use these models for text classification if you want to classify like text, but we won't get into natural language processing until next phase, unfortunately. But any problem, any data science problem that you want to solve that, you know, this is basically in contrast to regression where we were predicting on a continuous variable. These algorithms are mostly used for classification. A couple of them will actually, I'll mention it as we get there, but a couple of them have regression counterparts. So as we talked about before, in some cases we said that linear model may not be the best for predicting house prices. As we're going through some of these models have regression counterparts. And so when we get to those, we'll mention those as well. Does that answer the question?
Yes, thank you.
You're welcome. Anything else? All right, so I think something else to mention, just so you know the workload is not too crazy. For these topics, you'll see that each of them are like fairly long. And a lot of them you sort of see, not this one specifically, but you'll see things like building from scratch. My philosophy is that like these are not super helpful, especially right now, because I think coding from scratch is really just like they will give you the formulas and then you just have to plug it into code, but it doesn't necessarily help with understanding how it works. I would say like if these are like one of the algorithms that you choose to, you know, hone in on, maybe do those, but for the most part, a lot of these labs, I think the scikit-learn ones are good because they just show you the implementation. But if you see something that's like from scratch, I would say, I think this might be something that's from scratch too. Just read through and just make sure. I feel like those labs do take a lot of time. So in the interest of time, I would deprioritize those, just so you know. But these mostly come next week. So when we get to those, I'll put them in the homeroom so y'all will know. All right, let's get started with linear algebra. Really quickly, what we're going to talk about is why linear algebra. We're going to talk about the data types for linear algebra. This part we're going to do pretty briefly because these are just NumPy arrays, and so it will be a review. I think literally I created this lecture first, and I took that section and put that into our topic 4 notebook, so it's going to be a bit of a review. We're going to talk about operations, systems of linear equations, and finally, we can do linear regression with linear algebra, which I think that's a really, really cool application. So to start off, why linear algebra? So linear algebra is the basis of many machine learning models. When you think of linear algebra, I like to think of it as anything in multiple dimensions. If you have to do operations in like many, many dimensions, and a dimension being a feature, likely, especially in a data science problem, when you have like a bunch of features, you're usually thinking in a bunch of dimensions. Well, by default, data is already set up sort of like a matrix. You know, you have the 2-dimensional data structure here. You have your rows, your observations, and your columns, your features. And so sometimes you can use this like a matrix, and we'll talk about that later. Later, when we get into NLP, natural language processing, we'll be talking about how words can actually be represented as vectors, which is really, really cool. Something we'll talk about called word embeddings in the future. You can sort of see here the direction between man and woman is represented by a vector with this direction, and it's the same kind of direction, just parallel as from king to queen. And machine learning models have been trained to recognize these patterns, that like man to woman is somewhat synonymous to, is the word synonymous? I don't know. It's like similar transition between king and queen. And same here, we can recognize tense, which is very cool, from walking to walk, swimming to swam. And just depending on what models you're using, what pre-trained models you're using, and we'll get into this when we get into natural language processing, you can basically represent a lot of words. You can represent words contexts using vectors, which is really cool. Next off, images. Oh, why is my scroll like this? All right, images. If you don't know already, images are comprised of pixels, and in a black and white image, every pixel is represented by a number, and the number represents like the intensity of color. So in a black and white image, you have like your grayscale, and basically the higher the number, the darker the pixel. Images are also represented by tensors, and we'll talk about what tensors are later on. But in an image, you might have heard of like the RGB in an image, and basically that's a tensor, because you actually have 3 matrices, one for red, one for green, one for blue, and each pixel or each value within each color matrix tells you the intensity of red, green, or blue, and that creates your color image, which is actually really, I think is really cool. And we'll actually deal with some image data in phase 4 as well.
So will that be, images be a 3D tensor cube like they mentioned?
Yeah, so images are tensors, yep. So the second last application of linear algebra is used in some algorithms. And my favorite one is the recommendation system algorithm. And I'll talk about that algorithm in the next phase, but Netflix actually uses a very linear algebra based algorithm, which we'll talk about.
Do we have tensors more than 3 dimensions?
Technically you can, but I'm not sure if they're considered tensors as well. I've never had to deal with like concrete data types that are more than 3 dimensions. But I imagine, I don't know if they're called tensors, to be honest, but you can have arrays with more dimensions than that.
Thank you.
You're welcome. And finally, I think this is funny. I actually saw this on like I'm part of like a Facebook machine learning memes group, and they had this meme where I feel like this is very indicative of what we did, where before we learned linear algebra and multivariate calculus, we basically skipped all the way to doing like sklearn.linear model import linear regression. And I just thought that was kind of funny because the way that scikit-learn does their linear regression uses the gradient descent method, which we'll talk about tomorrow. The stats models version of linear regression actually uses the linear algebra formula that I'll show you all later. So I just thought that was kind of funny that, you know, there's all this like hard math that goes behind this that we didn't really talk about before we actually did it. But I feel like that's a lot of data science as well. So just really briefly, I wanted to just like do a quick review of the data types for linear algebra. You have scalars, vectors, matrices, and tensors. This is a pretty popular comic strip that I found, again, off that Facebook group. So really quickly, scalars are just magnitude. So any number is a scalar. A vector is an array with magnitude and direction. So a vector, you can sort of see it kind of looks just like a list here, and I'll run all of these. Actually, let me run these examples first. A vector has magnitude and direction. So the coordinates of the vector represent the tip of the vector, where the tip of the vector would be if you travel from the origin, and the magnitude of the vector would be its length in space. So let me just draw a really quick example of that. And I do see that I have some chat messages. Oh, can all our messages, yeah. I used to have a lot more time to create lectures on campus. I would have like weeks between each lecture I would have to give. So we'll see in time. I used to teach a lot more of the later phase stuff. So you'll see more memes coming back. So what was I doing here? I was drawing this. So let's do 2D just to start simple. So here we just have like something in 2 dimensions, and we're gonna call this dimension A and dimension B. So let's say we have a vector, and a vector is 2, 3. So in a vector, the number of elements represents the number of dimensions. So a vector 2, 3, and let's just assume that the first dimension is A and the second dimension is B. A vector of 2, 3 is saying that, all right, we're gonna move in the A direction by 2. So by 2, and we're gonna move in the B direction by 3. So 1, 2, 3. And then where do we end up? Let's hope this arrow works out the way I want it to. So we end up with a vector here. And this vector is 2, 3. And it's important to have the direction as well. Not super important for data science application, but in linear algebra, it's important. So this is what the direction is. So vectors, it says, where does it say? Magnitude and direction. So that would be the direction part. And the magnitude of a vector is just the length of the vector, the length of this blue line. And you would really just find this using Pythagoras' theorem. So this would be like the square root of 2 squared plus 3 squared. And there is actually a built-in function to do that as well. So that is a vector. Next we have matrices. They can be interpreted differently in different contexts, but often it's used to represent multiple simultaneous vectors. We'll talk about what this means in the context of something like linear regression later on. But if you think about like a data frame, I like to think of a data frame as a bunch of rows of vectors. So each row, you can think of a vector. And so if each row is something like this, each number is a value for each feature. So you can sort of think of, all right, every data point that I have can be represented by some vector in however many dimensions I have in my data set. If that makes sense. So yeah, often used to represent multiple simultaneous vectors. A vector or matrix can be multiplied by a scalar to create a change in scale and or direction. So what you can do is you can actually multiply vectors and matrices by a scalar. So let's say I can take like this times 2, this times 2, and it will just like double the length. And if I have a negative, it goes backwards. And tensors are just made out of matrices with the same dimensions. In terms of just like for Python coding purposes, vectors, matrices, and tensors are represented by Numpy arrays, not lists. And I think we talked about this back in phase 1, but Numpy arrays are good because of broadcasting. I'll talk about broadcasting later on as well. So here we can use numpy.array.shape to explore dimensions of data structures. .shape, exactly the same as what we were doing in data frames. And you can see here all of this output. This used to be a more interactive thing, so you can take this notebook and just like play around with the cells. This is what I wanted to show you all about the magnitude, the length of the vector. We have in Numpy a linear algebra library where you can find the norm, and they use the word norm for length, and you can find the norm of the vector. And this would be for vector 1, 2, 3, 4, 5, 6, would have a length of about 9.54. Questions so far? All right, I realize this might be a little bit small, so hopefully this is better now. All right, so the next thing that's useful to know, I would say for us, it might be more useful for like data wrangling and like editing data frames because we don't use transpose mathematically very much in data science, but just good to know that this exists. The transpose of a matrix will just flip the matrix. So it turns rows into columns, columns into rows. You can imagine sometimes you get like really messy CSVs. You might need to do something like this. I think transpose for our purposes is most likely gonna come into play with something like this rather than something mathematical, but good to know that the dot transpose method exists here, also exists in pandas. So that's really nice. So you can see here, I have this matrix that's just 1, 2, 3, 4, 5, 6. When I call dot transpose on it, it turned the rows into columns, and then the columns 1, 4 becomes the rows. That's just something that's good to know. You can also transpose, usually you're just going to transpose matrices, but you can also transpose tensors. You will probably never ever do this, but just interesting to know that when you transpose a tensor, it's confusing to me as well how the numbers shift, but something that's interesting is the shape order is reversed. So instead of 2, 4, 3, which is like 2 groups of 4 rows of 3, it becomes 3 groups of 4 rows of 2. So the shape order is reversed. I will say you probably will never do this, but just something that's interesting. Questions so far? I will say transpose comes back later on towards the end of this study group. So if anyone remembers when I ask a question, transpose might be the answer.
Is this kind of what happens when you do your dummy variables? You kind of transpose them into columns?
Oh, that's a good take. Not exactly, because if you're doing dummy variables are usually something from one column, and then you're you're splitting one column of like values into multiple columns.
Yeah. Okay.
But in a similar sense, I think, like if you had like, 1, 2, 3 here, and let's say that was like one column, and you wanted to like split it into like 3 separate rows, you would have that, but I wouldn't exactly call that transposing. Transposing for matrices at least, or anything 2-dimensional, I like to think of it as like if you have like a diagonal line from like top left corner to bottom right corner, you flip it that way, and that is always a transpose.
Thank you.
Welcome. That was a good clarifying question. All right, moving on quickly. You have operations on vectors and matrices. Just to start off easy, addition and subtraction. The addition and subtraction of vectors, matrices, and tensors work as long as the dimensions are equal. The operation will occur element-wise. So that means that if you have 2 vectors, v and w, v plus w will just be, the first element of v plus the first element of w. And then for the second element, it will be the second element of v, second element of w. So really quickly, let me do the plus example first. I have 2, 4, and 3, 2. V plus w, just automatically, you just have to give it the plus sign. Your array will end up as 5, 6. V minus w, pretty straightforward, same thing. It can go negative. So 2 minus 3, and then 4 minus 2 gives us this array. Graphically, I think this is kind of interesting, but let's just see what this looks like graphically. So let me draw really quickly this in 2D. All right, and let's just say, right, this is just X and Y. So to start, let's take a look at what V is. So V moves 2 in the x-axis and then 4 in the y-axis. So let's say that this arrow here is V. And then let me just annotate this here real quick. Use a different color. This value here is 4, and this value here is 2. Now we're doing V plus W, so let's plus W, which is 3, 2. So I sort of think of that as, all right, we're gonna extend from here because we're literally adding 2 vectors together. Let's see, we're gonna go 3 in the X direction and 2 in the Y direction. So it probably looks something like this. And then basically this vector will be, let me get this up, all right. So this will be whatever it is plus 3. So here we end up at, is that right? Nope, wrong order. Give me a sec. This one will be plus 2, and then this one will be plus 3. And then here you'll have 5, and here you'll have 6. And so graphically, this is what this looks like. And then the sum of these vectors can be represented as a new vector that sort of joins this into a triangle like that. So graphically, that's what's going on when you're adding 2 vectors together. Does that make sense? Cool.
Quick question.
Yeah.
It says as long as the dimensions are equal. If they're not equal, does that mean it's not possible or it's done differently?
If the dimensions are not equal, and by that, let's say like V, so right now V has 2 elements and W has 3 elements, probably what will happen, not in Numpy, because Numpy won't let you do that. Typically what will happen if, let's say you had, let's say 3, 2, 5, if you were to add this together mathematically, you would assume that this starts at 0 because nothing has happened in that direction yet. So mathematically, that's what will happen. It'll just create a new dimension and extend it by 5. But if I were to run this, I think it throws you an error because in Python with NumPy arrays, they see that the shapes are different. So V has no 3rd dimension. In math, you can sort of assume that there's 0 in that dimension, but you would have to put that in if you wanted to have like different dimension arrays. But yeah, that was a good question too. But yeah, because each of these, remember, each of these elements represents a different feature or a different dimension or a different feature. Hopefully that was helpful. That made sense.
Great, thank you.
You're welcome. Let's bring it back to this. All right. So addition and subtraction, as long as the number of elements is the same, if it was, you can actually expand these to matrices of the same shape as well, element-wise. Same thing will happen.
Excuse me, Ish.
Mm-hmm.
These are different features or different values because vectors have one column and multiple rows.
Yes, one column. Yeah. So that's a slightly different way of thinking about it. I think it really depends on context, the way you interpret a vector, just like the way you interpret a matrix. I like to think of this as, okay, in this data point V, let's say this is like feature X, feature Y. So feature X will be 2, feature Y will be 4, and that's the same for W. So feature X will be 3, feature Y will be 2. So these are different values representing, how far in each feature space V and W goes. Does that make sense?
Yeah, so we are considering this as 2 columns and 1 row.
Yes, I actually think that makes more sense. I know that in the labs it says it's like a one column thing.
Yeah.
Which is more like a series. But you can also think of a series as a vector, although because my understanding of this is like, vector, you're representing different dimensions and each dimension is a feature. Where if you just had a series, it's technically one dimension. Why would you put each observation in a different dimension? That's my take on that.
Okay, thank you.
You're welcome. So okay, we talked about this before, broadcasting. So I'm not going to go super into it, but let's just go over this really quick. Basically, you can broadcast anything of a slower dimension to a higher dimension, as long as the higher dimension array contains the same shape. So first example, I think we talked about exactly this in phase 1, but if you have a vector 1, 2, 3, 4, 5, 6, if you do vector plus any scalar, like here we're just adding 4, you just end up with 5, 6, 7, 8, 9, 10. And then for vectors and matrices, you can technically also broadcast vectors onto matrices. This will not work because the matrix doesn't contain the same shape. So here you can see the vector is 3 elements, but there's no like 3 element here. So this won't be able to be broadcast. What works is if we did it this way. Let's hope I don't make any typos. If we had it this way, then it can be successfully broadcast. So what we've done here, we've taken this matrix and we've subtracted 1, 0, 1 from each row of the matrix. So that's quickly broadcasting. Super quick exercise that I won't talk about right now. Just think about what shapes of matrices and vectors can be broadcast onto a tensor like this. Again, we'll very, very unlikely deal with like tensor operations, but that's what we have here. Questions so far about these operations? Nice.
I'm sorry.
Yeah, no worries.
What happened if we want minus M1. Can you do it?
V1 minus M1?
Yep.
I actually don't know if that will work.
Oh, equal. Yeah.
Oh,
Times.
cool. Yeah, I guess you can reverse broadcast too. Oh, that's awesome. Thanks for bringing that up. I didn't even think about that before. Nice. Anything else? Cool. All right. So next, multiplication. There are 3 different kinds of multiplication when you're talking about matrices specifically. So the first one is very straightforward. You have the Hadamard product, and this is just element-wise. So exactly the same as how we were dealing with addition and subtraction. The Hadamard product happens element-wise. So if we had 2 matrices, we can just multiply them together like that. And that one specifically uses, and let me just do the numpy.arrays, numpy.array, and then multiply by, and let's copy this over. This happens element-wise. So it's just a regular star for multiplication, same as we're doing with numbers, and you get that. The more important one, the more important one is the dot product. And so unless otherwise stated, if you're dealing with matrix multiplication, it usually refers to this kind of multiplication, the dot product. So it's kind of confusing for most people, I think, but basically think rows of the first matrix, columns of the second matrix. And so how we multiply 2 matrices together, you're basically going to take, all right, the first row of the first matrix, and actually let me circle that here. Oh, we'll rectangle it. We're going to take this first row multiplied by the first column to give us this first element. So you can see here we have A11 times B11 plus A12 times B21. So we're doing element-wise product within these parts of the matrices. And then you're basically going to do the same for the others. Hopefully this is clear, but if you have this as yellow and then this as yellow, we get this one. And then let's see if this coloring works. If we have green here, it gives us this product. And then finally, if we do the bottom row and the right column, we end up with this. And you're doing element-wise multiplication within those, I guess, those vectors within the matrices. This is something that I would honestly sit down and just stare at for a little while. I will say not very likely you will be made to do matrix multiplication, but I did get it as a question one time. Not exactly multiply these matrices, but I was asked this exact question. What are the shape restrictions to doing this matrix multiplication? I don't know if anyone has any ideas so far. So if I have 2 matrices, A and B, so let's say A is an M by N matrix and B is a P by Q matrix, what kind of shape restrictions do we have here? Knowing that we're doing some sort of element-wise multiplication.
M rows and Q columns.
M rows and Q columns. Nice. So your resulting matrix actually will be of M rows and Q columns. That's a fun thing to know. So your resulting matrix will be of M rows and Q columns. And then the shape restriction that you have is N and P has to be the same. So let me just write it here. N and P have to be the same. And resulting matrix will be M by Q. Honestly, the way I remember this was just by sitting down and doing a bunch of matrix multiplication questions. Tomorrow's warm-up question will be doing a really quick matrix multiplication so you get used to it. And I would suggest doing, this is something that I suggest just doing by hand with pen and paper, just to get used to it. But yeah, good for us that we actually have it built in as numpy dot dot. So with these 2 matrices here, with A and B, you actually have the numpy dot dot. You can do that with A and B, and it will give you the dot product for the 2 matrices. One other thing to notice is that because you're using the rows of the first and the columns of the second, the order of your matrices does matter. So let me just print this one first, and let's see how it's different from B comma A. So you can see here, we are doing the dot product in different orders, and you end up with different matrices. So the order of multiplication matters. Literally in linear algebra, you will say things like left multiply or right multiply, depending on which side you want to multiply your matrices with. So yeah, any questions about this? Yeah, I think this part in particular is something to like honestly just stare at for a little while, but I wouldn't spend too much time on it. If it's like making your head hurt, I wouldn't spend too much time. The last product we're talking about is the cross product. We're not going to use this at all. It's just good to know that something like this exists, but it's used for more abstract applications of linear algebra, and here we'll just define it for a vector. So cross product of two vectors, we actually use like the cross multiplication symbol in linear algebra. Using the cross and using the dot for multiplication are different. So for this one, you're usually using the cross, so cross product. And the cross product of two vectors is the product of the magnitude of both vectors multiplied by the sine of the angle that is formed between the two vectors, if that makes sense. So if you think about, let's say in 2D space, and let's just draw our 2D space again. In a 2D space, you can have one vector here and one vector here. These two vectors have an angle between them. And that's actually something that you can also calculate, but we will not for now. But the angle between vectors is something that can be calculated. Can be also calculated in 3D, technically, but abstractly in 4D and higher. But we'll just define it, but this is just for in vectors. You can see that, you know, some angle is formed here. And so that's what theta is. And they're also multiplying it by n. And this n part, as you can see here, n is the unit vector perpendicular to the plane formed by two vectors. Sounds crazy, but imagine that this was on the floor. If I'm drawing this on the floor and I have two vectors like that, any vector perpendicular to the plane formed by two vectors basically means that, all right, two vectors, you sort of like can form a plane. Imagine them like that and on a flat surface. Any n is any vector that shoots up out of it. And so you're sort of like creating a new dimension that way, but you're basically a vector that shoots out of it. Very abstract, so if this doesn't make sense, really don't worry about it. But that's what n is. And a unit vector, specifically, a unit vector is any vector that has a length of 1. That's just more of a definition thing. Not super important to know for this either. So the cross product and what this actually yields has a magnitude, has a magnitude or length equal to the area of the parallelogram formed by two vectors. This gets pretty abstract. So imagine that I have these two vectors here, and by what I mean by parallelogram formed is if I were to extend these, so imagine that these were parallel, the magnitude of this cross product is literally the area of this parallelogram here. So this entire area here. That's the length of the cross product. The cross product is also going to be perpendicular to the plane formed by the two vectors. So you can see here, as I was talking about that, you have that vector that shoots up from out of it. And so that will be what the result of your cross product is. Again, super abstract. I only mentioned it because it is in one of the labs, but I will say not important to know. If you'll never see this ever again, probably. But any questions about this? Okay, good. Lastly, division, which cannot happen with matrices. You just don't divide matrices. However, you do have an inverse of a matrix. So really quickly here, several things that we're going to talk about are every matrix, almost every matrix, but most matrices have inverses. And basically what an inverse of a matrix does is if you multiply a matrix by its inverse, you end up with what's called the identity matrix. And the identity matrix is the operational equivalent to 1. So I just think of identity matrix as like a 1. An identity matrix, what it looks like in matrix form, it looks just like this. So an identity matrix, and you can actually try this out and try multiplying matrices out. Identity matrices have 1s across its diagonal. And this in linear algebra is actually called the main diagonal from top left to bottom right. So those are all 1s, the rest are 0s. And if you multiply any matrix by a identity matrix, you just get the same matrix again. But also, if you multiply a matrix by its inverse, you do get the identity matrix. There are formulas for calculating the inverse of a matrix, but not important to know. So
can you give an Sorry, can you give an example of? Oh, is that what you're about to do?
Oh yeah.
Of like, yeah. Sorry.
Yeah. No worries. So here I have a matrix X, and that's a 3 by 3 matrix. And here I have the identity matrix, and you can actually very conveniently, Numpy has an identity method here, and 3 because I want a 3 by 3 identity matrix. So let's take a look at what this yields. This is our X. This is our identity matrix, so you can see 1s along the main diagonal. And then I took the dot product of both of them together. And you can sort of see, even though, yes, there's a decimal point, but it's the same. It's the same matrix. That's the effect of an identity matrix. Operationally, same as multiplying by 1. So after that, let's talk about the inverse. So again, great. We have it built in. There's an inverse method within linear algebra and Numpy. So we take a look at this. Oops. Let's take a look at this. This would be the inverse of X. And then here you can see there's a few layers going on here, but the main part is in here, I'm taking the X dot product with inverse of X. And you end up with, negatives because of the rounding error, but you do basically have the identity matrix. So that's just to show how the inverse and how the identity matrix play with each other. Questions about this? All right. So that's like crash course of linear algebra. We're going to get into applications really quickly. And this will lead into doing linear regression with linear algebra, which is, I think, really cool. So systems of linear equations, I think there's one of the labs has a good like answering questions in this style. And I think that's like a good one for like practicing, visualizing, your data frame as matrices. So as a quick sidebar, what are linear equations? And we actually talked about this with our linear regression. The result of our linear regression, our model, is a linear equation. So these are all linear equations because each unknown or each coefficient is multiplied by not anything more than a linear variable. That was not a good sentence, but you can see that our unknowns are only multiplied by a scalar and raised to a power of only 1. So here you can see, x minus 2y equals to 1. You just have plain old x, plain old y. They're multiplied by scalars. Here in this example where we have 3ex and 2 pi y, 3e is still a scalar. 2 pi is also still a scalar, so this is still a linear equation. These are not linear equations because here you have x with a squared. Here you have y being natural logged. Here, this part is linear, but this part isn't because y to the power of x is not linear. And here you have exponent of x, again, not linear. So let's solve a system of linear equations. So that's the first step of our application. So let's say we have this system of linear equations. And usually the number of equations that you have match the number of unknowns. So you can do this with algebra. I think most of you know how to solve this by doing like, substituting like x and then you substitute y and you solve and find out what x and y are. But we can do this with matrices as well, which I think is really neat. A little harder for especially something small like this, but it expands very well. So this system of linear equations, x minus 2y equals to 1, 3x plus 2y equals to 11. First, we need to represent these as matrices and vectors. This part I think is tricky for most people, like translating this to this and why that is the translation. So I like to think of this as, all right, here we have this square of numbers, right? We have 1, 3, -2 plus 2. This goes in here, x, y on this end. If you were to multiply out each column with each row, if you do matrix multiplication here, and we don't have too much time, but I'll see if I can draw it out. When you're multiplying this by this, you take x plus minus 2y. So it becomes x minus 2y, which is literally this part. And then for the second equation, you have 3, 2, and actually let me use a different color just for clarity. We have 3, 2 here, and we're going to multiply it this way. So we have our 3x plus 2y. And then because this multiplies out to this, we can see that the first equation will be equal to 1. The second equation will be equal to 11. And that's how we're going to equate the two sides. So really quickly, there's a bunch of like letters here that look kind of intimidating, but I'll walk through them. Let's first set up our A and B. Basically what we want to do is we want to solve for x. We want to find out what x is. So let's just call this one on the left A, this one on the right B. If we remember from like solving algebra, the way you solve for x is just by isolating it on one side of the equation, right? You want to get everything else on the other side. So this is what we start off with. A multiplied by x equals to b. This is how we start. What we're using here is the fact that we know that if we multiply a matrix by its inverse, it gives you 1. So what we're doing here is we're actually taking the inverse of A and we're left multiplying it on both sides. So that's why we see here we have A inverse times A times X equals to A inverse times B. So we have this here. On the left-hand side, the A inverse times A cancels out and becomes the identity matrix, or basically 1. And then you basically have X isolated, and that's solved. So if we do this really quickly, we have A and B here. And just for it to be a little bit clearer, inverse of A is done here. And all I'm doing is take the inverse of A dot product with B, and that will be our answer. So we have our answer as 3, 1. And let's just do a really quick check. X is 3, Y is 1. Does it solve the equations? Here, X is 3 minus 2 gives us 1. That solves. And then 3 times 3, 9, plus 2y, 11. So that solves. This also expands to bigger matrices. And the bigger matrix that we're going to deal with is an OLS problem. But before we move on, any questions about this?
Based on our earlier discussion, the vector capital X contains 2 values of X and Y, or it has 2 columns of X and Y.
Ooh, that's a good clarification. I would think of that as, in this case, 2 columns X and Y, which is, yeah. But this is really more for like mathematical use. The main.
But based on dot product rule, it should be 2 rows.
It should
right?
be 2 rows. No, actually, so let me just draw out. So the dimension of this is 2 by 2. And the dimension of this is 2 by 1. Oh, so yeah, what you mean by 2 rows, yeah, it is 2 rows. Yeah, but if you don't think of 2 rows as 2 features. So I think that's where it's confusing because of the different definitions depending on context.
Yes.
But yeah, so as you can see here, yeah, the inner dimensions, that's how I like to remember it. The inner dimensions have to match, and the resulting is the outer dimensions.
Okay, thank you.
You're welcome. Sorry for the confusion. Anything else? Okay. Next, we're gonna do this, but in the context of OLS. So just some quick recap. Linear regression can be interpreted as a solution for a system of linear equations. So you can sort of think as each observation being a linear equation. And the coefficients are the linear unknowns that we're solving for. And we'll look at that as a matrix later on. So we're representing each observation as a linear combination of features. So that's also similar to, like, the resulting model that you have, your y equals to, like, beta 0 plus beta 1 x1 is a linear combination of features. So yeah, our prediction equation looks something like this, which is a linear equation. Represented in matrix form, we'll have y equals to xb. So x is all of our data, and b is going to be all the coefficients that we're looking for. I'll set it up later on as well. And y is going to be our y values. So really quick, let's set it up with this car data set, because I think that's like one of the easier ones. And let us also drop the non-numerical columns. So let's see over here. We have 1, 2, 3, 4, 5, 6 columns. We have cylinders, displacement, horsepower, weight, acceleration, and year, and we're going to predict miles per gallon. So I like to think of this as a really large matrix, an XDF, and let's actually see what shape this has. Let's print XDF. Shape. So XDF is a 392 by 6 matrix that we're basically trying to solve. What we're trying to do here is, let me see if I can draw it really quickly on the side here. We have our Y, which is our miles per gallon. Miles per gallon equals to our X. And this X is this gigantic 392 by 6 matrix. And then we're going to solve for 6 coefficients. 6 coefficients, let's just make this into a skinny looking block. 6 coefficients and just one row of 6 coefficients. So you can sort of see how this will multiply out. And we want to find out what these are. And this is usually B. Does this need any clarification? So B is going to be just 6 coefficients that we're getting. The coefficients that come up in your summary table. All right, so let's see if we can keep this here. Hopefully it doesn't block anything later on. So once I have this, one really quick thing that I have to do that I won't get into, but I think I linked something down. Yeah, one of these I'll talk about later, but one of these has why we do this to account for the intercept term. We're going to have this data frame that just has this constant term here. So it solves for not just the 6 coefficients, but also solves for the 1 intercept value. So, all right, let's solve for B. And as we learned before, to solve for B, all we have to do is left multiply by the inverse of X. And that's what we did previously, so let's start with doing that. We're gonna run this cell, which is finding the inverse of X, and you can actually just plug in the data frame values like that, which is pretty neat. But you end up with an error. And it's saying that the last 2 dimensions of arrays must be square, which is kind of annoying. Something that I didn't conveniently mention is that you really can only find true inverses of a matrix if a matrix is square. There are other kinds of inverse that there's also like a left inverse and a right inverse, and those can be applied to like non-square matrices, but do not worry about that at all. Just know that for regular inverses, you can only find the inverse of a square matrix. So shoot, we can't do this. We can't solve this anymore. However, we actually did talk about some tools that we can kind of incorporate into this equation to turn this into a square matrix, which I think is super, super neat. So this is quickly linear algebra theory. Let's see. Invertible matrix. Invertible matrix is basically any matrix that has an inverse, and it has to be square. So n by n square matrix A is invertible if there exists an n by n square matrix B, such that this is equal to each other. So we end up with this equation, which I'm going to like really quickly derive. I'm going to leave this here, and I'm going to do that up here. Okay. So what we want to solve, and let me just grab a different color real quick. What we want to solve is we have y equals to x times b, and we want to solve for b. So what we want to do is we want to isolate b on the right-hand side. And because we want to isolate b, we need to find some way to get rid of x. So how can we turn x or get some sort of inverse to get rid of x? What we use, and you can sort of guess by here, we're going to use the transpose. So kind of convenient, we have the transpose of x. And let's just think about what that means. So let's say first, I'm going to multiply the x transpose to the left of both sides. So looks like I just complicated things. But what happens here is that this combination of matrices, whatever this is, will be square, because x is 392 by 6. 392 by 6. X transpose is 6 by 392. Okay, I don't know if me writing these numbers is helpful. But whatever these dimensions are, x transpose x, the multiplication of that is a square matrix. So convenient now. Now that we know that x transpose x gives us a square, we can actually take the inverse of x transpose x, which is pretty neat. So what happens is we have x transpose x inverse multiplied by x transpose y is equal to b. Because what I'm doing is I just imagine this inverse part is to the left here. It'll cancel all 4 x's out, and you have b isolated on this side. If this didn't make sense to you, really don't worry about it. You probably will not have to derive this ever. But just need to know that just with knowing that we have transpose, knowing that we have inverse, we can solve any linear regression problem just like this. So let's see. Let me clear this really quickly. And actually, no, I don't want to clear everything. Let me just clear this orange bit. So with this, I've got all the values coded out here. Here you can see I have x transpose. This is going to be x transpose x. So matmul is the same as dot product. And then I'm taking the product of everything. You can assume that these are all correct. And our b, which are our coefficients, are all of this. These are our coefficients. And so let's just take a zip to see what they correspond to. So these are the results of our OLS solved using linear algebra. Just as a really neat trick, we can compare. So what I'm doing here is I'm fitting the linear model with our scikit-learn regression. And you can see our numbers kind of match up. Our constant is -14 here. And our coefficients match up as well. So you can see -0.329. Here you can see 3.29, but divided by 10. And then so on and so forth. So it actually all does correspond, which I think is super neat. Just to quickly close out, a bunch of resources. Learning linear algebra theory will be helpful in the long run, especially if you want to take more of a machine learning engineer route. But for now, it is a lot. Linear algebra is an entire semester of college for most people. So don't feel pressure to like understand everything I'm talking about now. This is a super good playlist, 3 Blue, 1 Brown, really, really good series on linear algebra. This talks about the matrix approach to linear regression. It explains basically what I explained in the last 10 minutes, way more in depth. This is a cool interaction. This is actually a very interesting one because it talks about like, what about all those error terms in linear regression? How is it solving even though all of these points aren't on the line, and what those parts mean? So a bunch of resources here for you all. Cool. Any questions to close out? Awesome. Well, tomorrow we're going to continue with calculus. If you've noticed, there is no material on the GitHub because I will be just doing a lot of whiteboard drawing for that one. So yeah, let me know if there are any other questions. Let's see if there's, I don't think there's anything else I needed to mention. So everyone have a good rest of your day. Any questions at all, just let me know. I'll see you all tomorrow or at whenever our one-on-ones are. Bye, everyone.
Thank you.
You're welcome.